We're going to see examples of computing determinants a little bit later, so I'll hold off a minute for that. Let's talk about a system of n equations and n unknowns. What does that look like? Well, let's say we have variables or unknowns x1, x2 through xn. And if I write n equations, the first equation might be something like c11 x1 plus c12 x2. Let me change that. Let me use a's instead because that's the notation we've been using here. So let's say we have a11 x1 plus a12 x2 all the way up to a1n xn equals b1. That's one linear equation in these n variables. You'll see the indices here. The first one will here indicates equation number 1. For equation 2, I'll have a21 x1 plus a22 x2 up to a2n xn equals b2. And I keep going like that all the way to the nth equation, an1 x1 plus an2 x2 up to ann xn equals bn. How do we deal with a system of n equations and n unknowns? Well, first we can write it in matrix notation as ax equals b, where, as before, x is this vector x1, x2 through xn. Here, A is called the coefficient matrix, and it's just our matrix A11, A12 through A1n. It has the coefficients used in each of the equations, A21, A22 through A2n, all the way down to AN1, AN2 through ANN. And of course, the vector B for this system, B is our constant vector. It's just the vector B1, B2 through Bn. A theorem tells us, a theorem from linear algebra says that a system like this of n equations and n unknowns will have a unique solution if and only if the determinant of A is non-zero. So if you look at this coefficient matrix and the determinant of A is non-zero, when the determinant of A is non-zero, we say A is non-singular. Conversely, when the determinant of A equals 0, that means A is singular. So when the determinant of A is non-zero, then there will be a unique solution to this system. What happens when the determinant is 0? Well, then there are two possibilities. There might be no solutions at all to this system of n equations and n unknowns, but there might be an infinite number of solutions. And I'm sure you've all seen this in your linear algebra classes. Let's talk about what it means for a matrix to be invertible. The definition tells us the matrix is invertible, an n by n matrix A is invertible, precisely when there's another n by n matrix B with A times B equals B times A equals the identity. Here the identity, when we're talking about an n by n matrix, is the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0. Let me try to keep these lined up a bit better. With a 1. There are 1s down the main diagonal. There are 0s everywhere else. This is the identity matrix. One reason it's called the identity matrix is, I guess the main reason, is because when it comes to matrix multiplication, you can check that the identity matrix times a matrix A is just equal to A times the identity matrix, and that's just the matrix A itself. So it's the multiplicative identity when you're talking about multiplication among n by n matrices. When there's another matrix B, which has this property that AB equals BA equals the identity, then we say the matrix A is invertible, and we say that that matrix B that works is called the inverse of A, and we'll often write it like this as A inverse. Now here, related to the earlier theorem, A is invertible, and again this is for an n by n matrix, any square matrix. A is invertible if and only if the determinant is non-zero. And in fact, if you want to solve the equation we were looking at before, ax equals b, and let's say that the determinant of A is not zero, so A is invertible. One way to solve that is to know that A has an inverse, and if you happen to know the inverse of A, you can just multiply both of sides of this equation by the matrix A inverse on the left, and A inverse A is the identity, and the identity times x is just x, so you have x is A inverse B, and that tells you the solution to your system as just the product of the inverse of the coefficient matrix A times the constant vector B. Remember, this will only work if the determinant of A is non-zero, if A is actually non-singular or invertible, and if you happen to know A inverse. In general, however, it can take a lot of work to find A inverse, so this isn't necessarily the most efficient way to find the solution to a system of equations, but it tells you, in principle, what that solution looks like. So let's look at a quick example. Can we tell if this matrix is invertible? And if it is, what's its inverse? Well, we can do this a few different ways. Let's first try to just ask the question, is this matrix invertible? And one way you can do that is to compute its determinant. What's the determinant of the matrix 1, 1, 0, 0, 1, 1, 1, 1, 1? Well, we can expand along the first row. We start with the first entry, 1, times the determinant of its minor matrix, which is just 0, because 1 times 1 minus 1 times 1 is 0. Then we subtract the second entry of the first row, 1, times the determinant of its minor matrix. Notice that that matrix, I'll write it down here, we have the determinant of the matrix 0, 1, 1, 1. That determinant is minus 1. So we have 0 minus 1 times minus 1. This determinant is 1. What does that tell us? That tells us the matrix is invertible. Now, how in the world do we actually find the inverse? Well, here's something you probably learned in your linear algebra class. To find the inverse, you can create what we call an augmented matrix with the matrix A on the left and the identity matrix on the right, and then we'll apply row reductions. We'll talk about those in a minute, as many as necessary until the left side is reduced just to the identity. And what you get on the right side will be A inverse. Now, if A is actually invertible to begin with, it will be possible to use row reductions and reduce A to the identity, and then whatever you have on the right will be A inverse. It's not really necessary to check ahead of time using the determinant that A is invertible, because if you just try this procedure, if A is not invertible, you'll see that when you apply row operations, you can't reduce A to the identity. What you'll have will end up with rows of zeros here, and that will actually tell you, as soon as you get a row of zeros on the left side, a row of nothing but zeros on the left side, that would tell you that A, in fact, is not invertible. So how does that work out in this case? We create this augmented matrix, 1, 1, 0, 0, 1, 1, 1, 1, 1, and we put the identity on the right. And we apply row operations. Now, what are row operations? There are 3 basic row operations. One row operation is you can just interchange any 2 rows. A second row operation is you can take a single row and multiply it by a non-zero constant. say take this a row and multiply it by 7. You have to apply it to the entire row. The other type of row operation, the one we're going to be using most often, is row replacement. We're going to replace a row. Like in this case, we're going to start by just replacing row 3. So before I do anything, I'm going to leave the other rows alone. There's our first row, our second row. I'm going to replace row 3. You're allowed to replace a row by that row plus a constant times one of the other rows. In this case, we're going to replace row 3 by row 3 minus row 1 with the goal of getting a 0 here in that first position. So when I place row 3 by row 3 minus row 1, I take 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 0 is 1. And we have to do that the whole time here, minus 1, 0, 1. Now, you have all probably seen the algorithm for this. You want to start at the upper left, and assuming that's a non-zero number, you want to zero out things below it. If it's a 0, you want to interchange with a different row to make it non-zero. Once you've zeroed out things below it, you move down and to the right to this next position. You try to zero out things below it, which we have. Then you move down and to the right. And if that's non-zero, that tells us this is what we call echelon form. That tells us that we will be able to get to the identity in the end, which for us in this problem means that the matrix is in fact invertible. And we can finish up the process by trying to zero out things, now starting from the right and moving to the left, zero out things above this main diagonal. So to do that, I'm going to again replace row 3 with not row 3. Now I'm going to replace row 2 with row 2 minus row 3 with the goal of zeroing out that 1 there. So I'm going to leave the other rows alone. 1, 1, 0, 1, 0, 0, 0, 0, 1, minus 1, 0, 1. I replace row 2 with row 2 minus row 3, 0, 1, 0. Row 2 minus row 3 would give me a 1 there now, 1 and minus 1. And we're almost done because now I just go backwards here and I want to get a 0 above this second entry here. So I will replace row 1 with row 1 minus row 2. Row 2 and row 3 will stay the same. So row 1 minus row 2 gives me a 1, a 0, and a 0. This gives me a 0, a minus 1, and a 1. This is now the identity, so this matrix must be A inverse. So A inverse must be the matrix 0, minus 1, 1, 1, 1, minus 1, and minus 1, 0, 1. And you can check that A inverse A is 0, negative 1, 1, 1, 1, negative 1, negative 1, 0, 1, times A, which was 1, 1, 0, 0, 1, 1, 1, 1, 1. When you do this product, how does the product work? I haven't talked about that here in this video, but I'm sure you've seen matrix products. You take the first row times the first column, meaning it's like a dot product. 0 times 1 is 0 plus 0 plus 1. First row times the second column, you can see that's 0. First row times the third column, again, is 0. Second row times the first column is 0. Second row times second column. And then you can just go through and see that the product A inverse A is really the identity. And the other way around, you'll get the same thing. A times A inverse will also equal the identity. You can check that.